It's my pleasure to introduce our speaker today, Dr. Malcolm Ross. So Malcolm started his career with a bachelor's degree at Colgate, and then he came to UTIG to do his master's with the plates group before they were called plates. So I'm too young to understand exactly what that means. But while he was with that group, he did a lot of work on paleogeographic and paleoclimate reconstructions of the Caribbean and Gulf of Mexico. And he even helped run that group for a little bit during his time here before he went to Rice for a PhD. And after receiving his PhD, he's had a very interesting career working in industry, but also having close collaborations with folks in academia and smaller private startup groups. So Malcolm's worked in petroleum exploration, but pretty quickly turned his attention to more sustainable energy sources. So while his colleagues were out drilling $1 billion oil wells, Malcolm was looking at new up-and-coming technology to bring geothermal to a powerful and sustainable energy source. So that's what he's going to talk about today, the latest and greatest in geothermal energy. And I think it's really exciting because there's definitely a lot of work and things that UTIG scientists could contribute to the exploration and safe production of geothermal energy in light of our current climate crisis. So with that, I'll give it over to Malcolm. Malcolm, welcome back to UTIG.
Thank you very much. And thank you everyone for coming, and especially the people in the seminar room with me, braving this new world of hybrid seminars. It's fun to be back. I actually was the Shell liaison for plates. So I've actually been in the building for plates meetings. But yeah, my history with UTIG goes back to the 4920 campus from 1984 to 87. I should explain a little bit on this slide. You'll notice the Black Swan detector title and the photo of the Black Swan. That's the title I carry now, and it's a title I thought up while I was at Shell. And the origins of that is that my job at Shell was to stay out of what everyone else was doing, and for looking for technology that we wanted to avoid being blindsided by. So I was acting like a tripwire for things that Shell was not focusing on in the new energy space. And it was my job to put my hand up and say, hey, you know what? Some Black Swan event has happened in this technology or that technology, and we should reevaluate that technology. And so along the way, I did find 3 Black Swan technologies or areas. One was geothermal, and so I'm going to talk about that. But also in small and micro module nuclear reactors. I think that's the new area for nuclear. And then ocean power, not waves and tides, but rather deep ocean power. We're talking about like Gulf Stream kinds of power. And I brought those to the leadership at Shell and said, hey, we need to reevaluate these things. And they're like, no, we're focused, we're not going to do anything. So they were glad to have me out there acting like a tripwire. But once I tripped the wire, no one was willing to explode. So, and I chose this title also because I like the acronym BS Detector, because that's a big part of the job when you're out there looking at new technologies, because there's a lot of BS in that space. Yeah, so once I got into geothermal, I got involved with the University of Texas. The Geothermal Entrepreneurship Organization, GEO, was a Department of Energy funded program. It ends at the end of this month. But it was around encouraging entrepreneurship in the geothermal space and working with startups. I'm now working with the Bureau of Economic Geology to help them spin up some geothermal opportunities in Texas. I'm an adjunct faculty member at Rice University, where I teach GIS. And then I also consult with the Rothwell Group. So that's a little bit of that. I wanted to put this up. My mother passed last week. She was quite proud of me and our family, and I do this presentation in her honor. So you'll forgive me if I just do that in her memory. So it's just a little bit of grounding first in terms of definitions. Geothermal energy, of course, is the thermal energy generated by and stored in the earth. It comes from the origin of the planet originally, and the decay of radioactive minerals, vastly more of the radioactive decay than the planet formation stuff. And then there's geothermal energy stored by the sun in soils. But for us, I'm going to just eliminate that. And what I'm really talking about is that deep earth energy, not that swing of temperatures that you see in the shallow soil. And the premise I'm operating from is that traditional geothermal energy is cost-effective, reliable, sustainable, and environmentally friendly to make and create and distribute electricity, but it's been limited, and it's been limited by geography to those places that have high geothermal gradients. In other words, the heat is relatively shallow and easy to get to. And that is something like 9% of the surface of the earth. That's the Ring of Fire, it's Iceland, it's Hawaii, a little bit of Italy, a little bit of Turkey, that's a real, regional. And that was one reason Shell chose not to get involved, because it was just too small. And for us to spread geothermal out and scale largely, we need a black swan event. Not a COVID kind of black swan, but a technological black swan. And I'm going to talk about what I think a couple of those are. And I should also point out that geothermal gets lost in the fact that a lot of people just think it's about making electricity. But making electricity probably is not the best way to move forward with geothermal, unless you have the high enough prices to support it. Direct heat is almost 100% efficient. If you can just use the heat that you're producing to heat homes, to do industrial processes, it's 100% efficient. You're not wasting anything in the conversion. And you can actually make cooling from the heat with an absorption chiller and some devices like that. Electricity is always something less than 50%. So I think people need to recall that. And here's a way to reinforce that. We're right now talking about making electricity here in a couple of different ways that I'll talk about, but you can also do things like make hydrogen, enhance ethanol and biofuel production, biogas, but look at all these other things on here: lumber drying, refrigeration, fabric dyeing, aquaculture, and what's interesting about geothermal is you can daisy chain these things together in a value chain where you can make electricity, and the output, the waste product of that, is perfectly good for doing ice. And then the waste product of that is perfectly good for heating and cooling, buildings. And then from that, you can sterilize soil, and then from there, do a geothermal heat pump. And not only is that at a value because you can do optimization with that. So during the summer, it might be really important to do a bunch of cooling stuff. But during the winter, maybe you can switch over and be doing something different so that your resources are not doing nothing because you're seasonally, your demand changes. So this is like an AI kind of problem to figure out what the best arrangement of uses are. So just a little bit about traditional geothermal. Dry steam is what you think about is Yellowstone or that kind of thing, and where steam's coming out of the ground and you capture that and you spin a turbine and make electricity. More commonly, there's the combination of flash steam, which is basically you have fluids as well as steam and you have to separate them. And then you do the thing that you would with the steam, but then you also have this lower temperature fluid that you have to deal with. And generally all of that is re-injected. Either the condensed steam or the condensed steam plus the waste fluid is re-injected into the subsurface. And the problem that you're always worried about is that cold material leaking over into your hot source and ruining your opportunity because you drop the temperatures. There's also the most common and most expensive approach now is called binary cycle, where you actually bring the fluid to the surface and you have a heat exchanger where that heat is translated into a butane or an organic fluid that has a much lower boiling temperature. So you can bring water up that's less than boiling temperature, but you can transfer that heat into a fluid that is above the boiling temperature, and then it's not steam, but it's still a gas, and you can still turn a turbine and do all those sorts of things, condense that working fluid back to a liquid form, and then redo it. So that's what a binary plant looks like. That's how you generate electricity when you're below the boiling point of water. Same problem here, however, is you got to worry about that breakthrough problem. This is the most cutting edge part of geothermal now. It's called enhanced or engineered geothermal. It adopts a lot from the oil and gas world, where you drill down, you frack, take a rock that doesn't have fractures in it, fracture it, and then pump water through those fractures. So enhanced geothermal often takes advantage of natural fractures if they're there, but normally what it's doing is fracturing the rock. That is currently the state of the art. If you go out in the world for commercial plants, this is where the buzz lies. In fact, yesterday, the Department of Energy just announced, I want to say it was $12 or $20 million, 12 million more invested in EGS. EGS has some serious problems, as do some of the others, and I'm about to get to it. But here's another kind of geothermal energy. That's what we call hot sedimentary aquifer, where essentially you have a rainfall that's being recharged into permeable sedimentary section. You produce those waters to the surface. This is very common, for example, in the Basin and Range province. So we're going to actually talk about this in the Texas context in just a moment. So let's do David Letterman's top 10 list of the classic problems of traditional geothermal. And the number one problem, that if you can't solve this problem, you might as well forget solving any of the other problems, the cost of drilling and casing. Up to 80% of every geothermal project, and on the average is closer to 50%, is the drilling and casing cost. So if you can't drive that down by an order of magnitude, probably at best 50% at least, you might as well not do this. The next one is around heat flow. And again, this is around that geography thing. To keep drilling costs down, you want to drill as least as possible. So you're looking for high heat flow regimes, and therefore you're limited to 9% of the globe. Heat loss is another one, and that has to do with the breakthrough thing that I talked about, where if you cool that reservoir too fast, your economic viability goes down. Another one is exploration success. And this starts to get into things that the UTIG might be interested in. Up to 50% of geothermal wells drilled currently fail. They do not encounter the geology that was required to make them viable. And that's how EGS basically got started. They were drilling all these dry holes. Dry hole in the geothermal world is lack of porosity and permeability to flow that fluid naturally through the rock. This is when the wells are really expensive because they have to be big and they're drilling into hot rocks. And if 50% of the time you fail, you can understand why that's a huge challenge. Another one is water demand and water depletion and pressure depletion, where, for example, that sedimentary aquifer one, where if you pump that water, a lot of that water out, you could be very possibly deplete the pressure. You could also, the recharge might not be faster than your input, so you could end up depleting the water. Again, that's an exploration, geological, reservoir modeling kind of problem, but it's a big one, especially out west in the US, where water is a huge problem, and finding water to replace your water loss could be very challenging. There's also a huge environmental footprint problem here. Especially with an open system where you're bringing materials from the subsurface, you're flowing water through the subsurface, you're dissolving salt and metals and radioactive material and all sorts of nastiness. You're bringing it to the surface, you're dropping the temperature. What happens? All of that stuff precipitates out, right? You also have the problem in the steam of non-condensable gases, which is really CO2 mostly, and hydrogen sulfide. And all sorts of nasty things come up in that steam. And if you've been to Yellowstone, you've smelt it, right? You smell that very strong sulfur odor. And having an open system that brings that to the surface is just creating problems and expense for yourself. I talked about EGS and fracking, and you know the cultural problems around fracking. If your solution says, you know, I want to frack here to do an EGS, a lot of the world is going to say no. So that's a problem. Another one is around induced seismicity, right? If you're moving a lot of fluids through the subsurface, you are very often changing pressures, changing stress regimes, and intersecting the Moore's envelope, and boom, fracture, earthquake. There have been at least 3 full-scale, $10 to $100 million investments in geothermal plants that have been shut down because of induced seismicity. Pohang, Korea, Geneva, Switzerland, I think it is, it's somewhere in Switzerland, and just recently in France. And if you've invested $100 million, you do not want to get shut down by one earthquake. So understanding the stress regime and where things are faulting and why they're faulting and how your fluids are moving and creating or inducing those things is a big deal. And then there's the whole corrosion scaling discharge problem where you're bringing these fluids and steam to the surface that have sulfuric acid, different kinds of acids and metals and so on. That's again a huge problem. And lastly, safety, right? You're talking about high pressures, high temperatures. Can we deal with those in a safe way? Of course, coming from the oil and gas world, we always have the safety element in there. So you might say, well, forget geothermal. Wind and solar is so much easier, right? You don't have any of these concerns. You have a different set of concerns, which is a whole other talk. But here probably is the most fundamental challenge that didn't even make the list because it's behind the scenes. And that's energy density. A gallon of gasoline, and I'm not sure about all these units, 40 megajoules divided by the volume, 10 billion joules per cubic meters. That's the energy density of gasoline. Water, solar radiation is 1 billion times less dense. Wind, 10 million. The point is, you're dealing with a huge energy density problem. Hydrocarbons are so ideal because they have extremely energy dense. In geothermal, to get around this problem, we've got to pump huge volumes of water to make up for the difference in density. So back to the question, why would you do this? Well, here are some of the solutions. So the first one is Hyperscience's Hyperdrill. And this is a technology to solve problem number one, the drilling problem. And this is a technology that I'm actually a strategic advisor to because I believe in it. And what they're doing here is shooting a projectile through the center of a rotating bit. That projectile is moving at 3 to 5 times the speed of sound. That's hypersonic. And when you look at the kinetic energy related to that, 1/2 mv squared, you are shattering the rock in front of the drill bit. And so now the drill bit is cutting through shattered rock rather than native hard rock. And it means the drill bit can go 3 to 10 times faster than a traditional drill bit. There are field trials going on for this right now. And here are pictures from one of them. This is in Idaho. I visited in October of 2019. It's actually at the site of a silver mine. It's actually parallel to the shaft of the silver mine. So you know precisely what you're going into because you've got the silver mine right next door, 10 meters away. Yep.
Hey, Malcolm, the problem though is if you fracture the formation ahead of the bit, you make casing that hole a lot harder when you're done.
Yes, so good question. So Jamie's asking about what's the nature of the hole you create? Are you fracturing where you're going to later be casing and trying to keep the formation waters in control? In fact, almost all the energy is directed almost vertically. And in fact, what you're drilling is reaming, right? So what the initial experiments at pressure indicates that there is no interference of the rock. Yes. This is the site. This is the machine, and they in fact did a side-by-side test with a traditional drill and a hyperdrill, and they proved a 3 to 10 times increase in performance. I went there and deployed these geophones, wireless geophones, because I realized that the collision of this device is a near perfect seismic signal. And 2 years ago, something like that, I came and gave a talk about that. Sean Gullick caught on, Brandon Shuck caught on, and Tom Hess. And so we actually did a project here looking at the seismic signal. Brandon was the main author of that work. So I'm actually presenting Brandon's work here now with my encouragement. And I'm going to try to run this video because I want you to get a little bit of the sense for just how loud this is, because we're talking about seismic. So here is I guess the audio is not going to work, but it's just as impressive visually. So here the shot is about to fire. and you can see the dust is falling. There's a lot of energy going into the earth, and this is doing it every 15 to 20 seconds. And that source is moving down into the earth by a couple of feet, 6 inches to a foot every shot. So you've got an enormous energy impulse moving slowly down through the earth. How enormous? Well, here's 12 shots that I know the projectile weight, which is about 100 grams, and the velocity, which is measured using a very sophisticated measuring system, and the kinetic energy in kilojoules, 121,000, 119,000, 99,000. When you compare that to the Richter, it's not Richter, it's what do they call it? The moment magnitude. It's between a 2 and 2.5 on that scale. That's a lot of energy. Not all of that energy gets converted into seismic waves. It's heat, it's fractures, it's a lot of things, but a huge amount of that energy goes into the system. How much? Well, here's traces from it. We overwhelmed the system with the strength of that signal. Now, part of the problem was I had set these up as for a passive seismic monitoring system. So I turned the gain way up, and this system just overwhelmed those. But we did have some geophones that recorded a full signal. And here's just one of them for one shot. And you can see here the full trace and the power spectrum. And then if we look at the zoomed in, you can see the trace, and you can see that the frequencies are both between 15 and 35 hertz, with a big peak around 27, 28, something a lot on that. So that's a pretty low frequency. The reality is that's probably going to give us less resolution at very narrow bands of layers, but in fact it will give us deep imaging. And by the way, if we go back to these pulses right here, you'll see there is energy at 11 seconds here, and coherent energy at 6 to 7. Okay, well, there's a 2-second offset here, so it's more like 4 seconds and 9 seconds, but we very well may be recording MOHO reflections here, just in these 12 samples. So there is a substantial signal there. If we have a signal, well, first off, let's talk about repeatability. Here's 3 different geophones and the signal recorded on them. And you can see the signal is highly repeatable, but you notice between 1 and 2 here, there is a change in character. And what happened was the equipment changed. The projectile, the velocity, and in fact, we recorded in the data. But after shot 2, 3 to shot 12, those are really, really stackable signals. And that repeatability shows great promise for things like a reverse VSP, okay, for template matching techniques. And my thing I'm most excited about is passive emission tomography. If you have a source like this, you may be able to create an image in the subsurface as you drill. So I thought that would be exciting. While I've got the attention of seismologists, let's talk about induced seismicity. So this is Ridgecrest. There was an earthquake, a series of earthquakes between 5.5 and 7 at Ridgecrest. It's right here off of the Garlock Fault, right at the edge of the Sierra Nevada and the San Andreas system. And this is the COSO geothermal region right here. And the main shocks and all these aftershocks, you can see a strong shadow effect at the geothermal plant. And here's the zoom in area. The gray is the background prior to 2019. The blue is related to the 2019 event, and the diamonds are where the geothermal wells are. And here is a cross section. So down to 15 kilometers, there's a really big shadow associated with that COSO geothermal area. Well, here's a Coulomb stress model. And you can see that those earthquakes concentrate in the orange and red area, but in the COSO area, shadow. So this is not a Coulomb stress effect or anything. This seems to be related to the geothermal plant. And here's a graph of seismicity over time and the Coulomb stress over time. What you see, the black is in the region, the COSO region. The gray, again, is the background. And what you see, the plant started in 1989. You can see a big increase in induced seismicity and then a big drop. What they're postulating, and this is, I think I need to This Im et al. At Caltech are postulating a thermal de-stressing. So rather than inducing earthquakes, you're minimizing earthquakes. Not at the beginning time when you're moving a lot of fluid around and the system's trying to re-equilibrate and all that kind of stuff. But after time, when all you're really doing is getting heat out of the system, you are de-stressing that system. Interesting, a lot more work to be done there, but this is the first publication at Nature this year of a thermal de-stressing effect. Where it's important is what I think is the black swan in geothermal, and I guess I've got there we go, is closed loop geothermal. I hinted at it when I was talking about those problems. I kept saying open system. This is a closed loop system. And this is by this company Eavor that I am advisor to as well. And this is not ornamentation in the figure. This is their design. Vertical wells, 2 of them side by side, splitting out into multilaterals, 10, 15 multilaterals in the subsurface, coming back up, generating power, going back down again, and being completely closed, no interaction with the environment. And this has some very interesting effects, but relating to the thermal de-stressing thing, these systems only extract heat. So all you're doing is extracting heat. In fact, would you get away from that whole induced seismicity time and get into just reduced stress? So there's an interesting possibility that this may not induce earthquakes at all. It may reduce earthquakes. Here's the latest design. In fact, they decided they could take that 2-ended system, fold it upon itself, and do this all from a single pad, where you go down vertically, go out in like this fork shape kind of thing, and come back with this all from a single pad. So the footprint of this just got much smaller. And the idea here is to expose yourself to more rock volume. One way to do that is induce fractures with fracking. Another way is to drill it for yourself and maintain it. And what this will cost a lot of money. If you're going to case all those wells, if you have these vertical wells, if these multilaterals are 2.5 kilometers long, something like that, you're talking about 50 or more kilometers of pipe. What Eavor is doing is in the drilling mud, they are putting a polymer, a pH sensitive polymer. They are drilling down to the least porous formation they can find. And then they're using the mud, injecting the polymer into whatever fractures or pores there might be, and the pH drops and it solidifies. So it's essentially like a plastic pipe. It's casing while drilling into the least porous formation they can find. When I found out about these guys, my colleagues and I said, you can't do this. This is never going to work. So we co-funded a project in Rocky Mountain House, Alberta, where they drilled down 2.5 kilometers. They were about 2 kilometers apart, and they drilled down and connected 2 multilaterals. And they were able to connect those first try, end to end, 8.5-inch pipe, nose to nose. The second one, they took 2 tries. Okay, they had a strike. They kind of didn't quite get it right, but they proved to us, number one, that they could do this. Then while they were doing it, they did this polymer mud thing. And this happened in December of 2019. Since December of 2019, there has been no evidence of any leakage into the formation, from the formation into the closed system. There's been no sand coming up from collapse. There's been no pressure drops, no evidence of failure of what they call rock pipe, which is that polymer system. And lastly, so here's some pictures of that. And I think this is the most dramatic picture here. There's one well, you can't even see it from where a lot of you guys are sitting. You can't even see that other little kind of, that's how far it was apart. And they were able to meet end to end. So that drill and intersect thing, we said it can't be done, they did it. The pressure test said it can't be done, they did it. And then the last thing is they validated the thermodynamics. They did a thermodynamic model of this. Now, 2.5 kilometers, this isn't very hot. It's the West Canada Sedimentary Basin. It's the thermal gradients less than 30 30 degrees C per kilometer. So it's not very hot. So it's not a real geothermal prospect, but they did a model of it, and the model indicated that this system will continue to generate energy for 20 to 30 years. And here's how it'll behave. And then they went and did it in the real world, and the model was within 2%. So what that indicated to us is that, okay, if you take that same thermodynamic model and apply it to a higher temperature, in theory, it should work. The other interesting effect here, and they don't mention it, is that because you have the two vertical segments, one going down, one going up, the down-going one is cold, it's denser, and it pushes the fluid through the system. And the upgoing thing is hot and it is less dense. This has what's called thermosiphon effect, and it will push the fluid through the system with no pumps. In fact, it will push the fluid so fast that it won't heat up fully. You have to throttle the system back. You have to choke it back, or the fluid flows too fast. And that means you have no parasitic load for pumping in this closed system. And you can sell all that electricity that you would otherwise be using to run your pumps. Okay, let's talk Texas. This is a different style of geothermal. This is that hot sedimentary rock style. This is a study done at the Bureau, by the Bureau, in conjunction with the National Renewable Energy Laboratory in the late 70s and early 80s. This is Bebout et al. Don Bebout did this work. And what he found was that in the Gulf Coast of Texas, there are two fairways, one Wilcox, one Frio. There are a high volume of sand that are over 300 degrees, 140 centigrade, 100 to 200 centigrade, with a high pressure gradient. In fact, they're overpressured, and the permeability is above 20 millidarcies. So there is a system below our feet. Well, maybe not here in Austin. I'm usually in Houston. So, but there's a system below our feet waiting to produce hot water to the surface without pumps again. And the other thing that's interesting about this stuff, well, here's the Pleasant Bayou experiment. This was 1980s, using 1980s technology. They drilled 3.5 kilometers into the Frio. They found 150 degrees C. And in those waters, it was 100 standard cubic feet of methane per barrel of water. There's a super saturation of methane in those waters. It's an oil and gas province, of course it is. And they floated at 75 kilograms per second, and they ran it for a year. And what they did was just make standard electricity using standard 1980s technology for geothermal energy, but then they burned the methane, and they doubled the amount of energy that they could produce. So this one research well in the 1980s produced a megawatt of energy from 10,000 barrels a day in the Frio. And then the price of oil went up, and everybody lost interest. Okay, this started when the price of oil was low. But now there's a real interest in it. And I know at least 4 or 5 projects right now who are trying to exploit this exact opportunity in the Gulf Coast of Texas right now. And this is what it looks like. So here's a cartoon of it, drilling at about 3.5 kilometers to the Frio, up to that binary power plant, and then re-injecting it, but not into the Frio, because you want to do the breakthrough thing. You can pump into a nearby depleted oil and gas formation. And then you remember, I said it has methane in it. So you can separate that methane. You can burn it in a recip or spin a gas turbine. You can gather that heat. That heat is another potential source of energy. But then here's where it gets interesting. You can capture the CO2 as a point source of the methane that you're burning. The methane creates CO2. You capture that and re-inject it into that brine stream before you put it in the subsurface. This is a carbon sequestration project. And in fact, the initial analysis is that brine will support more CO2 than you will create by burning the methane. You could make a carbon negative geothermal project in this way. Take someone else's CO2 and sequester it. You can do lots of other interesting things, because now let's talk about daisy chaining. Remember, I talked about absorption chillers. So you could chain in an absorption chiller and sell chilled water for air conditioning and industrial supply. And by the way, chilled water will make the ORC, the binary plant, and the gas turbine more efficient, because I don't want to get into the physics of it, but there's a reason why having a cold side is important in these power plants. You can also drive its desalination system and produce potable water. And then the waste product is still the right temperature to do greenhouses and agriculture and that kind of thing. And then what about swapping out that whole methane system and instead just doing hydrogen production? Take that methane, split it into hydrogen and carbon black, both of which are valuable products, and never produce CO2 in the process. Use the energy and heat from the geothermal system to make hydrogen. In the Gulf Coast of Texas, there are a lot of customers who want hydrogen. By the way, you could just use the heat in a refinery to preheat the distillate before you pump it through the rest of the system. Right now, they're burning methane. They're burning their own product to heat that stuff in order to refine the oil. Why not preheat it geothermally? So there are lots of opportunities in the Gulf Coast. But, and now where we get to the geoscience. How much brine is there down there in these pods of rich, high porosity sands? Is it enough for 20 or 30 years? How big is the radius of effect if you're going to pump that much fluid? What will be the effect on the reservoir if you pump all that fluid out of it and don't replace it, seismically and reservoir flow wise? In the Gulf Coast, there's all these growth faults. So what's the size of the fault compartments? And what are these sealing faults, or are you going to have some sort of effect that's going through the faults? How will the reservoir behave if you're just extracting water that fast out of it? Will the brine temperature evolve? And by the way, if you're pumping all that fluid out and it's being replaced, what's the temperature of the fluid that's replacing it? If it's deeper, you in fact could raise the temperature of the I don't know, I'm not a reservoir engineer, but I'd love to see a reservoir model that would show how that brine would evolve from a temperature point of view over time. What will be the seismicity from what you're doing? How long will the geopressure last? Will you have 20 or 30 years of geopressure? What's the difference between going to the Frio, which is colder but shallower, versus going to the Wilcox, which is hotter and deeper? Or would you go to both and have a system that produced from both of them? What about fracking? Would you need to frack to improve the porosity? Maybe you'd have to frack after 10 years. We don't know. As you depleted the pressure, would you go through the bubble point of the reservoir, and how would that deal with the exsolving of gases and so on? There's lots of very interesting geoscience reservoir engineering question here. Here's another page. What about the sink? If you're going to inject a acetic brine into a depleted reservoir, how is it going to behave? What is the capacity of that reservoir? What are the pressures that you're going to have to go overcome? Because remember, it may flow to the surface for free, but pumping it underground is not going to be free. And then how will it behave if you inject an acid? Is it actually going to improve the porosity and permeability? And will that injection induce seismicity, right? We all know what the big problem with fracking, at least Oklahoma, was not the actual fracking, it was the produced water the water that was used in the fracking being injected into fault-prone areas. And will the wells, because of the acidity, will the injector wells have to be some kind of high, grade steel? And how is that going to affect the price? And then in general, the geophysics questions of mapping heat anomalies. Can you map heat seismically? Of course, temperature, of course, is going to be an effect on the elasticity, and therefore the Young's modulus and all that good stuff. What about electromagnetic studies? If you are trying to map brine is a very specific resistivity profile. And so will electromagnetic techniques allow you to map the brine in 3 dimensions? And then could you actually do 4D seismic here and watch the brine move as you were moving brine through the system, especially into the depleted reservoir, for example? And then can you make this work financially? Because geothermal is competing with wind and solar is dirt cheap. And your profit margins are going to be pressed. Are you going to have enough budget to spend on doing seismic experiments, for example? Another page for the geochemists in the room. I'm not sure there are many here, but maybe online. how is that brine going to evolve? As you bring it to the surface, drop the temperature, pull out methane, then induce CO2, are you going to have scaling precipitation? What's that brine going? How's that brine going to evolve? And there's the question of how much CO2 per unit volume that brine can support. The initial calculations were it's more than you get from burning the methane, but we need to prove that. And then what about any microbial effects that might happen as you change the temperatures and pressures and pHs and all that stuff? And then on the sequestration side, and this is for me probably the biggest concern, is if you're injecting that brine into the subsurface, into a depleted reservoir that's been drilled like a pincushion, every one of those pincushion holes has to not leak, or your CO2 is going to come back to the surface. So that's the biggest concern I feel like in the integrity of this system. You can't promise to be sequestering this CO2 for long term if you're trying to inject your CO2 into a pincushion. Okay, I'll leave it right there. That was 45 minutes. I hope you enjoyed it. I'm happy to take questions from the room. And then Constantino, how are we going to do online? Are you going to read those to me? Fantastic. Okay, I am happy to take whatever questions there are in the room. Start with a microphone. Brandon has a microphone. And Constantino will read some as well. Anyone? Yeah, thank you.
Yeah, I think in the interest of making things easier, we'll ask if there's any questions in the room first. So.
Yeah. Okay. Really nice talk.
Thank you. Your name?
I have a question. My name is Xiaohua. I just came here recently and a new research associate. And so when you look at a lot of these geothermal fields during production, usually you could see like ground is subsiding all the time.
Yes.
Because they're not recharging enough water.
Yes, in fact, I worked for Shell and did geothermal work there. And the thing that held Shell back was the Groningen gas field. I don't know if people know about Groningen. Groningen is the biggest gas field in Western Europe. It's mostly in the Netherlands. And there's been a huge amount of subsidence there because they've been producing the gas. And homes have been cracked, and there's a huge resistance now in the Netherlands to anything that might do something like Groningen. And so there is, besides the induced seismicity, there is the subsidence issue as well. And that's, again, a reason why I'm a fan of closed loop, because you're not taking anything out except heat out of the subsurface. And so, yes, absolutely, subsidence is a poor cousin to the seismicity problem, but it's your house that's having cracks in the wall due to subsidence related to you withdrawing more water than you're putting back. Yeah, and again, very possible in the Gulf Coast. Yeah, if we're pumping all this water out of the subsurface and shifting it some distance away, yes, homes will suffer. So I'm sorry, does that answer your question?
Yeah. And another question I have.
Could you hold the microphone up a little?
Yeah. Another question I have is that you talked about Pongpan where they shut down the geothermal field because of the earthquake. But later on this year at Ridgecrest, you also talked about the thermal distress. So
yep.
Can you comment on that? Is it two cases really different?
Well, I think it's a matter of time. When you're just starting a geothermal plant, like they were doing at Pohang and Geneva and in France, that's when you're moving the most water around and the system has not reached equilibrium. The COSO thing, the reduction in seismicity came later, like 15 years into the process. So that's why, again, closed loop is the solution, because all it's doing is not heat and not fluid, only heat. And so hopefully you miss that whole rise of seismicity part of the curve and just go into the declining seismicity part of the curve. Yep.
Okay, plenty of time for questions. Any more here from the in-person audience? Okay, so I'll read out some off from the chat. It looks like we got. We have one from Madi on slide 61 about the closed loop advanced geothermal system. How much electricity power is generated? It seems that megawatt scale power requires tens of kilometers of horizontal leg and absence of multiple stage hydraulic fractures.
Yes, so I think that it's going to vary a great deal, and it's going to need to be proven. There is going to be a paper, a theoretical paper, that's going to address this at the Geothermal Rising Conference next week. But the answer is that this system is introducing tens of kilometers of volume, rock volume, because you're doing this multilateral thing. So the answer is the indications are for one platform, one pad, that there are tens of megawatts easily produced. But again, it has to do with the geothermal gradient and how deep do you want to go? How expensive is it going to be to go that deep, et cetera. So I think the answer is it's going to be on a case-by-case basis, and it will only be done where it's economically feasible for the results to come in. I hope that addresses the question.
Okay, perfect. And looks like there's others in the chat, and I apologize that I read your question, Madi. I think we'll have capability of hearing it here. So there's another question from Peter Eichelpohl. So if you want to go ahead and unmute yourself, I think you can ask directly.
Yeah, Malcolm, this was a very interesting presentation. You talked about the thermal distressing at COSO, and I would argue that thermal effects can go both ways. They change the stresses, and that can either induce more earthquakes or it can reduce earthquakes. I mean, it can go both ways depending on the geometry relative to the fault. But I would also say that is typically secondary to the direct pressure effect. So pore pressure changes tend to trump thermal effects in general. Now, then you said for the Canadian project that you don't see the risk of induced seismicity, but you still have the thermal effect, obviously, right? So that could potentially cause some seismicity, and that would have to be simulated and modeled.
Yes, absolutely. And the plan for the next commercial project, which is supposed to be in Geretsried in Germany, they have already spread out an array of geophones, and they are recording now the background. And then when the Geretsried project goes live, the drilling in March of next year, and then for the long term, it will be monitored and this question will be addressed. Because yes, absolutely, you draw down the temperature, you creating thermal gradients in the subsurface, which could be quite steep and indeed could produce seismicity. My prediction will be that they'll be very, very small. I don't imagine you're going to get magnitude 2, or above from a thermal gradient kind of induced seismicity, but that's only my prediction.
Thanks.
Thank you, Peter.
Okay, we'll move on to the next Peter Flemings.
Hi, Malcolm. 2 questions for you. My first question is, at Cornell, they have a DOE experiment. Can you hear me?
Yes, go ahead.
Okay. At Cornell, they have a DOE experiment where they're going to drill one well, inject fluid. It's going to transport through the formation. They're going to produce the fluid, and then they're going to recirculate it.
Yep.
I don't think you really commented on that technology or its potential. You have any comments?
Okay, that's the first question. I'll take that one first. Yes, John Tester is the godfather of geothermal in the United States, and he's at Cornell. And indeed, they are doing a project there, and they are supplemented by the fact that there's a lovely glacial lake there that's going to provide the cold side. So they are going to have greater efficiency because they have the cold side, and they have cold winters. I grew up there. Okay, I know how cold it is. I know people have gone to school up in that area who know how cold it is in the winter. So there is a project going on there, and they are talking about drilling into basement to get the thermal gradients that they want, and that will be challenging, hoping that the rock is going to be fractured enough to allow flow. But they may have to induce it, and New York State is one of the states that has a fracking ban. So there are going to be some challenges to Cornell. By the way, University of West Virginia is doing the same thing, thanks to the fact that Joe Manchin is the senator on the Energy Committee, and they are putting a little bit of pork into the state of West Virginia. And I think South Dakota is also going to do a similar sort of thing, all at university sorts of settings. So it's a blend of research and commerciality. I should have mentioned, or did I mention that the seismicity project, the hyper drill thing, I talked to the CEO earlier in the week, and he is all in on doing an experiment at Divine, at the BEG drill site south of San Antonio. He wants to do a couple kilometers hole and instrument it. So there may be a connection for UT at there. It's not a geothermal system yet, but at least on the drilling side.
And the second question was in your Gulf of Mexico example, what fraction of your energy is from the geopressured fluid drive versus just the hot water that's coming out of the ground? And let's not worry about the dissolved methane. I was just trying to understand, is your energy from the overpressure or is your energy from the temperature of the water that's coming out?
There's a possibility of both, in fact. You can spin a turbine from just the pressure, but the indications from the Pleasant Bayou experiment was you got vastly more energy from the thermal content of the water rather than the kinetic content of the water and the methane content, the burning of the methane. So yes, there is a opportunity to do that, but I think the indications are it's going to be a small component.
And my last comment I'll leave is it seems like one heck of a lot of water, and you got to put it somewhere.
Absolutely true. Yep. And that's why I think it needs places like the Bureau and the Institute to really validate the subsurface piece of this. These are a lot of engineers who are not really familiar with the subsurface, and I think besides the pinhole, the pincushion problem, there's an induced seismicity problem. No doubt in my mind. We got to address it, but yeah, I think there's plenty of research to be done there. Thank you, Peter. Anyone else?
Yes, the next question is from Cody.
Hey, Malcolm, really nice talk. And actually, my question feeds right off of what Peter asked. It's just generally like just a range. Like, what is the range in produced fluids from the hydrothermal examples you have, or the geothermal examples you have, relative to conventional or unconventional oil and gas produced fluids? Order of magnitude difference.
What range of what? Temperature?
No, the produced fluids that are going to come out from these geothermal sites. Like, how much water are you producing in one of these wells? They're coming out of the hole.
Right. So this gets back to that energy density problem. The more water you can produce, the more energy you're going to get to the surface. And the answer is, see, I guess Pleasant Bayou had the numbers there. They were talking about 41,000 barrels a day to produce a megawatt. Okay. Now, how much? I think the answer is going to be driven by the geology. How much will the geology allow you to produce? The answer is the more the better. At some point, you're going to be producing too fast. You're going to have collapse. You're going to have all sorts of geological problems by the amount of water you're producing. So it's going to be controlled, and it's going to be different in different places depending on cement and pressure and a lot of things. So, but absolutely, yeah. I listed those challenges, and one of them is understanding the effect of moving that much water around in the subsurface.
Thanks.
Yeah. And by the way, I'll mention that I'm just speaking to a student at the Colorado School of Mines who has identified 5 different play types in Texas, only one of which is the geopressure play type. There are others that do not require geopressure, do not require moving this amount of fluid. In fact, some of them are closed loop opportunities where you would have none of this effect. So Texas is not out of the game if we can't do the geopressure thing. Let's just be clear. But they all are going to require geoscientists. Go ahead.
Perfect. We have another question from Mohsen.
Yeah, thanks. Malcolm, thank you for the nice talk. I wanted to follow up on the Divine experiment that you mentioned. It seems like that the hypersonic tool creates a lot of noise and potentially seismic events. I mean, have those been worked out in closer to urban settings? Is there any permitting issues with that? I know you mentioned the Divine test site. I'll be happy to talk to you about this a little bit more, but have those like environmental noise issues, have they been considered in your schemes for
Yes.
the company you mentioned?
Absolutely. In fact, what's interesting about hypersciences, and the reason that I'm involved with them, is not really entirely geothermal. Because they have the capability to launch projectiles hypersonically in a very inexpensive way, not only can you drill a hole, you can make tunnels. So they have, their biggest customer right now is a mining company who wants to drill mines. Their next experiment, in fact, I don't know if it got funded or not, but was to drill a tunnel under Sydney, Australia, okay, for a roadway, okay? And by the way, they have already completed a NASA experiment where they turned the thing up and shot things into orbit, almost orbit. They weren't allowed to put things into orbit, but you can get payloads, small payloads, but payloads nonetheless into orbit using the same technology. So they have probably multiple revenue stream. The most difficult one is the one that I'm trying to keep their feet to the fire on, but there is definite opportunities beyond that. Now, the road company in Sydney absolutely was concerned with the seismicity problem in an urban center, underneath an urban center. And the experiment, Brandon made a presentation to the people about this exact thing. And the answer is, we can only make predictions until we go do it. We're not going to know what it is. And by the way, the other reason that this guy, CEO of Hypersciences, is interested in Divine is they would love to be part of the tunneling efforts that are going to go on here in Austin for mass transit. The Austin Shuck would be a lovely target to blast through hypersonically.
Okay, great. We should talk about Divine. Definitely, we should talk a little bit more about Divine when you have time.
Yeah, absolutely. Yep. Thank you, Mohsen.
Thank you.
Okay, and we have a comment in the chat from Alexandros. Would you like to unmute yourself and ask?
Yes. First of all, Malcolm, thank you very much. Great talk. It's really very interesting. I just want to add something on the discussion about the case of Ridgecrest compared to other cases. So in the case of Ridgecrest, we have the situation of a geothermal field in between in a very active tectonic zone. And in case of Strasbourg, things have been much different. That was more like an isolated case. This is a non-active tectonic zone, so we didn't expect to have any seismicity. So I think that's what actually happened. The French team there were not expecting something to happen. But going back to the recent case, it's really interesting to see. I mean, we have created a video where you can see the evolution of seismicity with time, and you will see that with such a big earthquake, there are a lot of rupture zones that have been activated through time. So that's why you see there is not one clear fault zone that we identify there, but there are more than one. So that's really a very interesting case, which actually the idea of having a geothermal field in between that might, let's say, take the force and of any type of stress changes in the area and let's say decrease any influence. That really it's interesting to follow up.
I have to say, I'm sorry, I couldn't hear that. Could did anyone understand the question there? Or is it in the chat?
There's no question, Malcolm, just a description about what's actually happening in two different cases. And the Ridgecrest case is a little bit of a mixed bag of what's happening with the stress changes and the seismicity that we see, which is much more complicated than a simple case like the Strasbourg case.
Okay. Comment on the complexity of the Ridgecrest.
Yeah, and one of the attractions of the closed loop system is it does not require faulting or any of that stuff. You can drill into a placid sedimentary basin, unfaulted or minimally faulted sedimentary basin, and get away from any of those concerns related to existing structures. You're not looking for fractures. You're really looking for the least permeable layer, the hottest, least permeable layer you can find. Okay.
So with that, it's 11:31. So I think we'll end the seminar there. Thank you all so much for coming. And let's say thanks to Malcolm again.
Thank you, everybody.